So this is the baseline dynamics model. And I'll go into some detail about what each of these terms mean, just so you can have some background knowledge about this. So the first expression here, okay, let me take a step back. So U, V, and W are the velocities in the helicopter's frame. So U is the forward velocity, V is the sideways velocity, and W is the vertical velocity. Sorry, U, V, and W dot. Okay. And then P, Q, and R are the angular rates. So it's roll, pitch, and yaw. So let's look at what these terms mean. So this first term for U dot consists of V and R. So what this is saying is that if the helicopter is moving sideways and then it rotates along its vertical axis, that sideways velocity will turn into forward velocity. Okay, so this is just predicting what's going to happen if we're moving in a direction and we rotate a little bit. Second term is the same thing, except it's in the vertical direction. Right? So if the helicopter is moving upwards and then it pitches forwards, it'll start going forwards. And you've got similar terms for both of these, for all three of these, U, V, and W dot. The last term here is a drag coefficient, essentially. Sorry, the last term is drag coefficient. And there's also a gravity component, which is just the component of gravity that's aligned with each of the axes. Right? So you've got the forward, sideways, and vertical axes. In addition, for the vertical axis, it's not simply a drag coefficient, but we also have a control input that exerts influence on this axis. So I collective is a control input. So if you imagine the helicopter is hovering and you increase the collective, it'll go upwards, essentially. And then there's, again, the same drag coefficient. And lastly, there's this offset term. And what the offset term, offset term represents is simply that the controls aren't perfectly centered, and so you need to be able to compensate for that. And so although CU, CV have one number each, CW is actually a vector that contains three numbers. Okay, so for PQ and R, it's very similar. We've got one control input for each of these axes that controls how fast the helicopter will rotate in each axis. Similarly, we've got a drag term and an offset to compensate for the fact that the controls aren't perfectly centered. Yeah, so we don't model any airflow or any of that. Yeah. And we'll get into how this could possibly work soon. Okay, so let's look at what happens when we're using this model. So what this plot shows you is the x-axis here is time, and the z-axis is error. So what we did is we took our model, we predicted what the helicopter would do in response to our control inputs, and we compared it to what it actually did. Okay? And so you notice that the errors are huge, right? So at this point, that's roughly 3 Gs of error here. So it's like 30 meters per second squared of error here. And so if you tried to fly a helicopter using this model, which you saw earlier, essentially, it crashes. Okay? Yeah, 3 Gs of error at that point. So there's a key observation that helps us deal with this. So here we've plotted the actual error for a few different flights. And if you look, there's a pattern. And maybe you have a hard time seeing it at this point. But let's see what happens when you align the trajectories using the algorithm I described earlier. Now the pattern is much clearer. And so there's a lot of consistency in how our model is off for a given type of trajectory. And so as a side effect of the alignment algorithm described earlier, we have a way of aligning these errors. And so this will give us some insight into how we can use these errors to get a better model out, essentially, right? So now we're saying that we've got these trajectories we want to follow. We know that it's going to be off by 3 Gs at this point in the trajectory. And so we can just kind of add that in. Right? So if we follow the same trajectory repeatedly, the errors are consistent over time after the alignment of the data. And so why is that? Why does that work? And this gets to your question a little bit. And that's that we think what's going on here is that there's a few unmodeled variables that we just don't have sensor data for. And we think that the net effect of those variables is the same for the same flight over time. Right? So the airflow around the helicopter, the actuator delays, and many other variables that we're not modeling. So as you saw in that plot, that kind of holds, right? The net effect is roughly the same for different flights. And the intuition here is kind of the same as what human pilots have with muscle memory. It's not like the human pilots know the airflow around the helicopter. They don't have any sensors to let them do that. It's that they know how the helicopter reacts when they fly the same trajectory over and over again. So what we're doing then is learning trajectory-specific local models. So we've got data that's aligned in time. We can weight by the time to exploit the repeatability of the unmodeled variables. So what we're doing is, at each point in the trajectory, we're trying to say how far off our model will be, the baseline model will be. And what we do is we take a window around each time, essentially, and we say that we're going to average over that window. And it's not quite that simple. We use a weighted average that doesn't actually have a sharp cutoff. And what this gives us is a model for each time for each maneuver. So let's see what that does. Before I go into that, I'm going to talk about our experimental setup a little bit so you have an idea of what data there is and what exactly is going on. So the helicopter's pretty much off the shelf. Our human pilot built it for us, but there's no modifications to the helicopter itself. We put on an inertial unit, Microstream 3DM GX1. It provides data at 333 hertz. It gives you magnetometer data, gyro data, and accelerometer data for all three axes. For some of the later examples I'll show you, there is a RPM sensor, and so that tells us the blade speed. And we've also got sonar on the helicopter, so we can tell how far the helicopter is from the ground. We've also got these offboard cameras, and what we do with offboard cameras is we track the position of the helicopter. And you might wonder why we don't use GPS, and the reason is that when the helicopter is flying as fast as it does, the GPS starts to lose its signal lock. Also, when the helicopter is flipping, you might imagine that it also has trouble keeping a signal lock, right? Because now the helicopter is in between the satellite and the sensor. The computer is off board. It's not on the helicopter, and the only reason for that is essentially weight considerations. And also, if it crashes, we don't lose the computer. And the computer is running an extended Kalman filter, and what that's doing is it's taking in all of the sensor data, the sonar, the inertial unit, the cameras, and it's outputting the state of the helicopter, an estimate of the state of the helicopter. Also running on the computer is the receding horizon differential dynamic programming controller. And I'll break that down a little bit to give you some idea of what exactly that means. So what's going on with, what's the exact setup that's going on here? So we've got a controller that's sending signals to the helicopter at 20 hertz. How do we pick what controllers are sent? So this is where the receding horizon part of the controller comes in. What we do is we simulate for some horizon, in this case it's 2 seconds, what would happen if we sent a sequence of controls for those 2 seconds. So essentially, since it's 20 hertz in 2 seconds, we pick 40 sets of control inputs to give to the helicopter. And we pick the best 40 at the given time. And then we send the first one. And now it's a new time step later. And we rerun the process. We don't send the second time step from the 40 we just computed. We recompute a new set of 40. And then we send the first one of those 40. And we keep doing that until the trajectory is completed. And the reason for that is this lets us account for deviations from the trajectory that we might have encountered, right? Let's say the control that we sent wasn't the best control, actually. If we just sent the same thing we computed a second ago, or a tick ago, or a 20th second ago, then we'd be sending suboptimal controls, because now we have more information about where the helicopter is and how far off from the trajectory we might be.